Parseval's theorem. Parseval's theorem is one of these things that just makes sense when you say it in words, and yet mathematically it can seem very complicated. In words, it's that the average power, remember we're representing that as a capital P, since it's an average, it's a number, it's not a function. The average power P of this periodic signal, and let's pretend it's a voltage, and it's the voltage going into a 1 ohm resistor. This way we can really talk about what power means. Is it's equal to the DC average power plus the sum of all of the AC average powers. So that just makes sense. Now let's write it in terms of math. The power P, you already know that if you've got that signal, the same signal, the V of t, if you find its RMS voltage and you square it, then that's the same thing as capital P. That's the same thing as average power. You work this out in signals too. In fact, that was really the definition of what VRMS was, is it's what the equivalent DC voltage would have to be in order to have the signal produce the voltage signal produce the exact same power. And in our last online lecture, I pointed out that that's also equal to this formula. What Parseval's theorem says is that this integral on the left is equal to your choice of, here's our DC average power, plus here's our summation of all of the AC average powers. Or another way to say this exact same thing, if you've got your Fourier decomposition in rectangular components, is little a sub naught squared plus 1/2 times the sum of all those different harmonics of this. Because after all, a sub n, capital A sub n squared, is just equal to little a sub n squared plus little b sub n squared. So this RMS thing, this isn't, I want to just point out, where is this coming from? This seems a little bit like magic at first. This is not magic. This is just a result that it's the same thing as VRMS times IRMS times cosine of theta V minus theta I. And that's what we remembered from the last board. And if we're doing it through a 1 ohm resistor, then our current is the exact same thing as our voltage, and they'll be in phase, so this goes to 1, and that's where our VRMS squared value comes in. I'm going to get rid of this now. I'm going to get rid of that aside, so we can focus on our key result. And this is the key result, that power is this. This is Parseval's theorem, that this integral and this sum are the same thing. So this gives you the power to do two very important things. The first is that it lets you compute VRMS very quickly if you know your Fourier series breakdown. Because once you know your Fourier series breakdown, you know these components. You just sum them up Take the square root, and that's your VRMS. The second reason that it's important is that it lets you see how much, let's say, what percent of your total power is at a specific frequency.